When we think about the most fundamental breakthroughs in science, we always come back to Isaac Newton. In the 1600s, Newton didn't just watch an apple fall and get inspired, he laid down the laws of motion and gravitation. Equations so elegant that they explain everything: why planets orbit the sun, how a baseball arcs through the air. But here's the wild part. Newton's equations aren't just for big things, they also let us peer into the tiniest realms of reality. Welcome to the world of classical molecular dynamics, where we use Newton's laws to simulate the motion of atoms and molecules one by one. So what is classical molecular dynamics, MD for short? Imagine you have a box full of particles, each representing an atom or a molecule. Every single one of those particles interacts with its neighbors. Attraction, repulsion, collisions, they're all there. Each force adds up to produce a net effect, and Newton tells us exactly how these particles should move. How does it work in practice? We set up the initial positions and velocities of all the particles. Then, using Newton's equations of motion, we calculate the forces acting on every particle at a given instant. Next, we update their positions and velocities, step by tiny step, simulating their dance through time. This isn't just a static picture, it's a full-blown movie of atomic motion, frame by frame. Now, why do this instead of just running experiments? Well, some things are just too small, too fast, too complex to observe directly. With molecular dynamics, we can simulate how a protein folds, how a virus attaches to a cell, how a new material behaves under stress. These simulations help us see the invisible, letting us test ideas and make predictions long before anyone heads to the lab. And the impact? It's huge. In chemistry, MD helps us decode how molecules react, how drugs bind to their targets. In physics, we get to explore the properties of new materials at the atomic level. Even in biology, we can watch the inner workings of cells unfold in ways no microscope could ever reveal. The beauty is that all of this is powered by Newton's ancient insights brought to life on modern computers. So, the next time you hear about a breakthrough in nanotechnology, drug design, advanced materials, remember, there's a good chance it all started with a simulation built on centuries-old laws. Newton's equations keep shaping our world, from the vastness of space down to the tiniest atom. Thanks for joining us on this journey from falling apples to the frontier of science. If you found this fascinating, stick around, the universe is more dynamic than you might think.